G'day everyone, Peter Sobby back again with another Peltier inspired video. This time I want to talk about something that sounds a bit crazy. I want to cool our roof space here with a bank of Peltier, 16 Peltiers, powered off a solar panel, a single solar panel. Now the reason it sounds crazy is if you look at the raw numbers of the amount of heat that's coming down from the sun, at midday it's about 77 kilowatts, so the area of our roof is about 77 square meters viewed from directly above. And the Peltier-based system, let's say we get 300 watts from the solar panel, COP of 0.5, that means 150 watts of cooling. So 77 kilowatts, 77,000 watts versus 150 watts of cooling. Most people would say not a chance, it's just not going to work. And yet it does actually work. Now I'll explain at the end of this video why it does actually work, the numbers, the maths, the physics and science of it. But I do want to just show you the actual results just to prove that it does work. Before I do that, I just want to give some background here. We've had an incredible heat wave here in Japan. It's basically the same as the rest of the world. 5 consecutive days of just continuous sunshine, temperatures over 37, 38, 39 degrees. It's just crazy. And on the second day of that heat wave, at the end of the day, I just got inspired to install this system up there. It's been something that's percolating in my head for the last couple of months. I've run the maths a few times and it sounds like it should work. So I just really wanted to try it out with this heat wave. And so I did it. I went up on, I think it was Wednesday nights. I started around 9 o'clock at night here. I was meant to be doing something else, but as you do, you know, kind of get distracted with other projects when you have more important things to do. But anyway, I started lugging all this stuff up to our third floor balcony, just a small area, and there's a little door that you can go inside to the roof space there. And so setting up stuff up there, I did it very roughly. I didn't do any of the normal sensors and stuff that I would have here, so I don't really know exactly what's going on. I'm just guessing what should happen based on experience. So I put it all together. It's definitely not optimal, but it still worked fairly well. Like it surprised me how effective it was. So with that in mind, I want to have a look at the actual results first, and then I will explain how it all works at the end of the video. All right, let's get into it. So I've been getting data from a local weather station here. It's about 2 kilometers away and fairly representative of the temperatures here. I've got 8 days worth of data. That's 2 days before the heat wave, the 5 days of the heat wave, and today, which is the 8th day. It's actually 4 o'clock in the afternoon at the moment, but by the time I finish editing, I will have the full data for that. Now, the temperature data itself was a bit noisy, so I've run that through a moving average filter. It's over 50 minutes, and using that, the peaks over the heat wave were between 36.5 and 38.5 degrees, so pretty high temperatures even with that moving average. I believe some of the real peaks were over 39 degrees and a record for that weather station. Now the temperature itself, of course, it's one thing. The real problem is the sunshine. I'll put that up there on the graph, and you can see during that heat wave there it was ranging between 12.5 and 13.5, just constant sunshine, no clouds, just zooming down on that roof and just applying all that heat. So that's really the biggest factor, not so much the actual outside temperature. Now with that, I can now overlay my temperature inside the roof. I have a sensor sitting up in the apex of the roof. It's sort of, I'll show a photo of it. I didn't want to move that around because I wanted the continuity of data from before the Peltier system was set up. So that was just continually recording data. And of course, it will have a peak during the day and a minimum. As soon as the sun goes away, the thermal mass of everything that's in there, the wood and stuff like that, all of our junk that's up there, that will pull the temperature down. As well as nighttime, you do get a bit of outgoing radiation and just convection because the temperatures are now cooler outside. So with that, you can see clearly a trend line going upwards. The peaks are getting higher every day by 1 or 2 degrees, and also the troughs are getting higher. So with each consecutive day of heat there, it's just going up and up and up. So where it would end, I don't know. But on the around midnight on the second day of the heat wave, that's the 4th day of the graph there, you can see, if you look at the line closely, the rate of change is changing. So there's a kind of elbow there. You can see it speeds up a bit with the cooling. So that's when I've I've turned on the Peltier system. Of course, at night time, I'm running off just a normal power supply at about half the rate that I would get from the solar panel. And already we can see with that relatively light amount of cooling over maybe 7 hours, the second peak is already much lower. Now keep in mind that this, where I'm measuring it, is nowhere near. It's like 3 meters away from the Peltier setup, so it's not like it's blowing directly onto the sensor or anything. It's totally different space. So that drop in the trough there is quite significant. And then the peak on the next day is just way lower than the previous peak. It's about 2 degrees there. So I don't know the numbers yet. I haven't analyzed them, but I'll put that up on the screen when I finished doing the editing again. On the second day of my Peltier system, I kind of stuffed things up a bit. I was playing around with some evaporative cooling. I left the hot side heat exchange just sitting out directly in sun without any shade cloth or anything like that. So I kind of messed up a bit. So the troughs and the peak there are the same as the previous day. So I was getting some cooling, but just not the most effective cooling there. By the third day of the Peltier system, I've got it everything in gear, fixed all those little problems and stuff. And you can see again the peak, even though it was a super hot day again, the peak is now down again from the previous day, and the trough is also down again by a significant amount, possibly 1.5 degrees down from the previous day. So it's working fantastically, surprisingly well. It's very clear that the Peltier system is working. So now it's time to explain exactly what's going on here. How can it do this kind of cooling for such a large roof space area with that 77 kilowatts of energy coming in, or power coming in? The real story is just modern insulation, modern roof construction. That metal roof combined with the spray foam insulation underneath, that only lets through about 1.5% of that incident radiation that's coming in. So that 77 kilowatts, it really turns into about 1 to 1.5 kilowatts of actual heat going into the roof space, which is kind of amazing, and it's really the key to the whole story here. Now, of course, that 1 to 1.5 kilowatts, that's the peak as well. Over the 24-hour cycle, you probably expect that to average out to be about 300 watts. This is including the nighttime cycle where you actually release some heat back to the nighttime sky. So all of that together, I'd guess about 300 watts on average. Now that doesn't sound like much, but if you have 300 watts in an enclosed insulated space, it's got nothing else to do but to raise the temperature of all the stuff that's inside there. So 300 watts applied day in, day out. It's a bit like global warming. You will get that 1 degree to 1.5 degrees of increase every day, and that will build up so that your whole roof space gets to that 40 to 45 degrees. And then that in turn impacts everything that's underneath it. The bedrooms that we have underneath there, their ceiling's going to be warmer. You'll get the radiant heat coming down from there. It does feel a lot warmer. So cooling that space, putting the effort in to get rid of that 300 watts is absolutely worth it. So on the Peltier side, that's a figure of 0.5, of course, that was just picked out of the air. Real heat pumps, including air conditioners, the COPs are all over the place depending on the conditions of use. And this particular condition of use, where you've got very low DT between the hot and cold sides, it's probably going to get a COP of around 2 if it's built properly. At the moment, I guess I'm probably getting a COP of 1.5 because I've just slapped it all together, and I haven't really optimized water flow and heat exchangers and stuff like that. But in the end, I should be able to get about 600 watts from that 300 watt solar panel there. So that will easily offset the 300 watts coming in and also apply a bit of cooling. And you can see the results in the tests that I've already done. It's almost as if it's doing 600 watts at the moment. So perhaps I could get even more once I optimize things up there. All right. Now I did want to explain. So some people will be claiming that, well, if you've got a hotter temperature inside the roof space and it's cooler outside, maybe you've got 40 degrees here, 35 degrees outside, well, you can just go for passive cooling. Unfortunately, passive cooling just doesn't work very well. It's very hard to actually move, hundreds of watts of heat via passive cooling, and it's also temperature dependent. Heat pumps don't really care about the temperature difference. You could have a positive temperature difference where it's helping and you might get 550 watts out of a system. You might flip it basically the opposite and you get 450. But basically a heat pump wants to do that, that kind of core 500 watts of moving heat from one place to the other. They don't really change a lot depending on the temperature difference on both sides. The other thing is that the reason why this is such a great application is because the natural DT is a negative DT in the conventional sense. This is where you have the TC is the cooling side and TH represents the heating side. The natural DT there is probably around 5 to 10 degrees depending on the time of the day. And although the system does have thermal resistances that will probably turn it into a positive DT, it's not a very big one. It's somewhere in the range of say 0 to 10, in which case the Peltiers can achieve a COP of 2 or more. So that's basically the explanation of how we go from that 77 kilowatts to just maybe 300 watts, and the Peltier system can actually do around 600 watts of cooling for 16 Peltiers. Okay, next I'll just want to explain a little bit about the system itself and just wrap it all up. Okay, just a quick explanation of this system here. Of course, it starts off with a Peltier bank. This is a little bit of a different style here. It's a 15 Peltier bank. The one upstairs is 16 Peltiers. And for that one, I've actually used 3 of these for each bank, or a sub bank, I guess. So each one of these has the cold is facing inwards to a center block. So I have 4 Peltiers on each side of this, the cold facing in. So effectively 8 Peltiers coming into here. And then on the outside, on the hot side of those, there is 2 of these as well to collect the heat on the hot side. So that's a basic construction there. As I say, it looks similar to this in the end, but it's just a little bit fatter because of that extra layers in there. And so that makes just a nice compact block of 8 Peltiers there. And then I've got 2 of those to make the whole bank of 16, just connected with some tubing and stuff similar to here. So I did want to make a couple of points here that if you want to do serious stuff, you do really need to get a clamping system going. So just grab this guy here and bring it up to the camera a bit closer there. So I've got a clamp here for each individual Peltier. For that other configuration will be for each 2 Peltiers because they're all in line, and that's just super important for keeping the efficiency of the Peltier. So of course you have thermal paste. I'm also sanding these down to be flat, not too crazy, but just to get some of the edges off here, and then put it all together with the clamping there, and they work really well. The other thing with the clamping is that it gives you an opportunity to cable tie these away. These are like really easy to break, and they can degrade the performance a lot if you get a little bit of a resistive joint in there. So having that opportunity to cable tie all those in there so that these wires here, for example, are just the lead wires. I can move those around. They're not going to affect the wiring here for the actual Peltier itself. So that's the main Peltier bank itself. And I've gone with that 16 Peltiers. It's actually electrically connected in 4x4 configuration, and I've done that deliberately to match with the solar panels. So solar panels are a really good, let's say, synergy with Peltiers, because solar panels produce current. They're basically fundamentally current devices. Depending on the incoming photons that are coming in, they produce a certain amount of current, or they try to. And then the Peltiers, of course, are current-based devices, so the 2 of them just fit together really nicely. But you do need to do a little bit of maths and stuff, a bit of modeling through together a few different combinations. You have to have a kind of neat combination, like a 4x4 or 5x3 or 3x4 or something like that. So after a lot of modeling, I come up with the 4x4 seem to fit a 400 watt panel. And of course, a 400 watt panel under strong sunlight on a hot day doesn't get 400 watts. These panels that I've been using here get about 275 under that really hot summer condition. And in this particular application so far, I'm getting about, I think it's 250 watts, so a little bit above 8 amps. So that's be 2 amps per Peltier, so that 8 amps divided by 4 would be roughly around 2 amps per Peltier, and the voltage is about 30 volts, so you're getting somewhere around that 240, 250 watts actually getting pulled from the panel. So it's roughly a good fit. Based on rough figures, say a COP of 2, that means I'm probably getting around cooling of 500 watts and 750 watts on the hot side that I need to deal with. So that brings to the next point, of course, which is that on the outside I do have the box type heat exchangers. This is sort of made with a few of these guys. So 4 of these built into a box and fans fitted to the end. Seems to work really, really well. But of course, it is moving hundreds of watts. You know, it's not like 200 or 300 watts. It's like 500 watts and 750 watts. So they're just on the edge of being probably a bit too small size. So I would like to put maybe a second one of those in to just lighten the load a bit. I have also added in an evaporative cooler. This is on day 2. I stuffed it up at first, but eventually got that going quite well. Evaporative cooling, it's another case of just a great synergy between that and the Peltier. So normally we would say evaporative cooling in Japan, you're crazy, but on the hot side of a Peltier or a heat pump, any kind of heat pump, it's a really good match there. So you don't have to worry about the actual temperatures of the liquid circuit itself. What you really want to do is to get rid of heat, and the evaporative cooler can do that just really, really well. I'm estimating my system might be around 100 to 200 watts for that, and I'd like to improve that as well. All right, that's it. I think I've talked way too long. This was meant to be another short video. It always ends up way too long. But I hope it's been interesting, and I will come back in the future with a sort of more refined system and with a lot more measurement and stuff in there so I can tell exactly what's going on and how to optimize it. All right, hope you enjoyed it, and I will see you next time.